In this video, I want us to think a little bit about polarity, electron density. Basically, are all of the electrons evenly distributed throughout the atom or molecule, or are they kind of more focused in one region? And so you got to think about this kind of holistically. Both, what is it that you're looking at? Because we've got ions here and atoms and molecules, but then also electronegativity. It's going to play a big role because if you're more electronegative, you're pulling more of the electrons closer to you. And so then you also have to think about electron geometry. How is everything distributed? Is it pulling it such that it's going to act like it's a non-polar or polar and that kind of thing? So meaning, let's look first at sulfur. Sulfur, it's an atom. It's got electrons all around it. How is it going to act? Does it have a charge? No. Okay, so whenever we think about sulfur, we're not going to be thinking about it being polar or anything like that. Okay, here we've got a calcium ion. So it's even more than polar, if you will. It's an ion. And so an ion is kind of the extreme of polarity, meaning the electrons were so unevenly distributed that calcium broke apart from whatever it might have been ionically bonded to. And so ionic bonds are kind of like the extreme of polarity, where the electron density became so uneven that something popped off. That's actually why your acids work. And so when you're thinking about like hydrochloric acid, you've got a hydrogen bound to a chlorine, both nonmetals, right? So you would think covalent. But hydrogen and chlorine is so electronegative, it just pulls those electrons away from the hydrogen and the hydrogen pops off as an H+. And so that's what you're thinking about. Those ionic bonds are just an extreme of polarity. Okay? What about silicon tetrafluoride? It's got a central atom attached to 4 atoms around it. And these 4 atoms are all the same atom. That's essential in polarity. It has a tetrahedral electron geometry. Remember all that from way back when? So meaning it's going to be polar. Think about the fluorines all pulling equally and oppositely. If I swapped in any chlorine maybe for a single fluorine, now it's going to be polar, because fluorine is going to pull electron density differently than a chlorine. So since it's symmetric, it's going to be nonpolar. All right? Same thing for here. Very, very, very symmetric. And so your oxygen is going to be very nonpolar. So I'll kind of write that here. Nonpolar, nonpolar, etc. Okay? So now let's think through this. Once again, this is ionic bond. Okay? Does it have some polarity? Absolutely. But if you think about just this entity and just here, those bonds are distributing so well that it looks like it's going to be nonpolar because you have that trigonal planar electron geometry and you've got 3 oxygens around it. So it looks like nonpolar. But if you look at the molecule as a whole, that's once again the extreme, because you have an extra electron here and a less electron here. And so it's going to have electron density that's so separated that you're going to have an ionic bond here. And so in that case, it's kind of the extreme of polarity. It's almost as if by stealing that electron, it made it so it could be nonpolar within its covalent organization. Okay, so I know there's a lot to think about with polarity, and so I just want to get you start thinking about polarity, because polarity is going to make a huge difference and determine boiling point, intermolecular forces, okay? And those are going to be huge in this semester. And so I want you just to start thinking through, like, where is the electron density, and try and picture and see what's happening in these things and in these molecules and in these atoms and ions.